In this last section of Chapter 4, we're going to revisit velocity and acceleration like we first started in the last section of Chapter 2, but we're going to be doing this from the viewpoint of integration. So just a quick review of what we learned back in 2.7. If we're given a position function, which is usually given as x as a function of time, if we want to find velocity, we need to take the derivative of that position function. If we want to find acceleration, we would either need to take the derivative of velocity, or you can look at that as being the second derivative of position. So now that we've started Chapter 4 and learned about going backwards, now we can take that and apply it to these velocity and acceleration problems. We can use antiderivatives or integrals to work backwards if we're given acceleration or maybe velocity. So if we integrate acceleration, we'll be given a velocity function. Except I guess we're just going to have to keep in mind anytime we integrate, we need to put that plus c, or I guess I should say anytime we integrate without bounds. So by, I guess, logical extension, if we integrate a velocity function, that would give us a position function. But then we'd have to add that plus c because, again, that is our constant of integration. So once we kind of introduce this idea of integrating and working backwards, and now that we know integrals represent areas under curves, we need to talk about the difference between distance and displacement, because that's going to play a part here. So distance, I think we all kind of understand as just the total I guess length something covers as it moves. If an object always moves in one direction, then distance and displacement are the same. So then how is displacement different than distance? Well, displacement takes into account where you start and where you end. So direction does matter when we're talking about displacement. So just one little note to make here. However, if an object changes direction one or more times, total distance traveled and displacement may be different. So in general, we're usually going to be asked questions about distance. Very rarely are we going to be asked questions about displacement, if ever. So this is going to be the important one. And luckily, distance, I think, or total distance traveled is something we all kind of understand. So hopefully these two examples will illustrate real quick the difference between total distance and displacement. So if someone walked 1 mile from home to school and then walked back home from school that same mile, then how would distance and displacement differ? Well, distance or total distance would be 2 miles. They walked 1 mile to school, they walked 1 mile back home from school, so the total distance they covered was 2 miles. But displacement takes into account direction and the starting and ending point. So displacement in this case would be 0. They started at home and they ended at home, so their displacement turned out to be 0. Let's suppose someone walked 2 miles, doesn't really matter where, and then walked back 1 mile. Well, in this case, the distance was 3 miles. They walked 2 miles, and then they walked another mile, so that's just 3 miles. Very easy concept. Displacement in this case, though, takes into account the starting and ending position. So they walked 2 miles, and they backtracked 1 mile, so that would make their displacement 1 mile. Okay, so like I was saying in the last slide, once we introduce this idea of integration into these velocity and acceleration problems, we have to also be aware that integration means area under a curve. So to kind of do this, we're going to focus on our velocity curve, but we're also going to look at all three at the same time so we can kind of compare them. So if I were to first give you a position function here, we would know that the slope of that function is velocity, because we know the derivative of position is velocity. But the major graph we're really going to want to be concerned with is a velocity graph. If you're given a velocity graph, we know that the area under the curve and above the t-axis, normally the x, but in this case the t-axis, would represent total distance. And that's key, because the integral of velocity would be giving us a position or a distance. The slope of our velocity function would be acceleration, which is what we saw back in chapter 2. If you were given an acceleration function graphed, then what would the area under that function be? Well, again, we're thinking about area as being an integral. And if we integrate acceleration, then that would mean velocity. So that kind of relates by saying that the area under an acceleration curve is equal to velocity. Okay, a few more things we have to kind of solidify before we can take a look at a few examples. If an object moves along a straight line, that's all we're going to be looking at, is just straight line motion. When velocity is greater than 0 or positive, we define that as moving right if it's horizontal or up if it's vertical. If velocity is negative, we define that as either moving left if it's horizontal or down if it's vertical. And something we saw back in 4.4 still holds true. The area under a curve represents an accumulated rate of change. And that's key. As we move across this graph from left to right, we accumulate or add up the areas. So when we're talking about displacement, we're talking about taking into account the direction of motion. So if we're doing that, we know that areas above the x-axis, or the t-axis in this case, are positive, and areas below the t-axis are negative. So since we want to take into account the direction of that motion when we're integrating velocity in terms of finding displacement, we want to count area below the x-axis to be negative, or the t-axis to be negative. So to find displacement, if you're given a graph, you would take areas above and areas below and subtract those. So we get A1 minus A2 plus A3. But distance is a little bit different. Distance would be the absolute value of velocity. And the reason it would be the absolute value of velocity is we don't want to kind of take direction into account. We just want to figure out how much length in total was covered. So we don't want to count those areas below the t-axis as being negative. So that's why distance is still an integral, but it's the absolute value of velocity. And really the only thing that changes in terms of these areas is that anything that's below the t-axis would be counted as positive. So instead of A2 being negative, it would be positive, and we would still add them all up. Area 1 plus area 2 plus area 3. So these areas are again representing either distance or displacement, depending on how you look at them. Okay, so let's take a look at an example. We have a particle moving along a line, and its velocity is given by this equation measured in meters per second. We want to first find the displacement during the time period from 1 to 4. So we're going to go ahead and take a look at a graph of this, even though it's not going to be too helpful since it's a curve and we really can't use geometry to find the areas here, like you saw on that last slide where we're just adding up areas. So to find displacement from 1 to 4, I'm going to graph this equation just from 1 to 4. And you can see that there's going to be some area below the x-axis and there's going to be some area above the x-axis. So just to make sure we're interpreting this picture correctly, since velocity is negative from 1 to 3, we know this particle is moving to the left. Since velocity is positive from 3 to 4, we know that this particle is moving to the right. And if we kind of have to guess, even though we're going to do these problems, but if we just had to guess, in terms of the total distance, or I'm sorry, the displacement, is there more negative area or more positive area? Well, it looks like there's more negative area below the x-axis. So if we had to guess, our answer for displacement will probably be a negative number. So let's see if that's true. So displacement is the integral of velocity. And in this case, it's the integral from 1 to 4, since we want to find the displacement from 1 to 4. Our function is t squared minus t minus 6, and of course we can just simply integrate this without much issue. We'll get t cubed over 3, we added 1 to the power divided by that number. T becomes t squared over 2, And 6, the integral of that becomes 6t. We're going to put no plus c, of course, because we're integrating from 1 to 4. So we'll put this bar here, or the bracket, and then put our lower bound and upper bound. We need to plug in the top bound first, plug in the bottom bound second, and subtract. I ran out of a little space here to show that work, or that step, but we've practiced it a lot since 4.4, so just keep in mind we're plugging in the top bound first, plugging in the bottom bound second, and subtracting those two values. And sure enough, like we guessed at the beginning, we're getting a negative answer. There's more area below the x-axis than above the t-axis, I should say. So we know that that answer should be negative. And again, that's okay for displacement. Displacement takes into account the direction of motion. The way we're going to finalize this answer is to kind of write out a little statement here to show that we see what's happening. And since we're ending up with a negative answer, we know the particle moved 4.5 meters to the left. Now distance. The only difference between displacement and distance is we want to take this area below the t-axis and count it as positive, so we can find the total amount of length that was covered by this particle, or the total number of meters in this case. So how do we integrate an absolute value? Well, you can kind of take what I said just a moment ago and use that to figure it out. If we want to take a negative area and make it positive, we just need to put a negative in front of that piece. So the integral from 1 to 3 should give us a negative answer because it's below the t-axis. Since we don't want that to be negative, we're going to put a negative symbol in front of that integral, so it'll make it a positive. And then we'll add to that the integral, or the area, from 3 to 4, which is already positive, so that's why we're just going to add it. After that, it's really just the steps you saw from above. Our velocity equation is still t squared minus t minus 6, and the integral of it is still the same like you saw before. T cubed over 3 minus t squared over 2 minus 6t. Except now we just have two separate pieces that we have to do, so it's a little more messy than the displacement, but it's still essentially the same problem. So for this first value, we're going to plug in 3 first, we're going to plug in 1 second, subtract those two values. If you want to pause and make sure you can get these same exact numbers to be sure about it, then I would do that. When you plug in the 3, and when you plug in the 1 and subtract those numbers, you get negative 22 over 3, which we already knew. We know that that area being below the t-axis should make it a negative. But with that red negative I put in the front, that'll turn it positive, which is what we want to do in terms of finding the total distance. When you plug in the 4 into the second part, and you plug into the 3, and subtract those two values, again, you might want to pause and make sure you can get these values. You'll get 17 over 6. When you combine those two values, you get 61 over 6, or in this case, this particle approximately moved 10.167 meters in total. Okay, this last set of examples are going to illustrate the two ways you should be approaching the way you solve problems. These two AP test problems are essentially asking for the same thing, but we're going to solve these two problems using two different methods. So kind of keep that in mind as we're looking at these two problems. They're essentially the same, but we're going to use two different methods to solve them. So in this first example, we have a particle moving along the x-axis. Its velocity is given by the equation. If the particle's position is x equals 7 at time equals 1, then what is the position of the particle at t equals 2? So in an ideal world, I think we would have been given our position function, and then we could have just plugged in the value of 2, and we would have been done. Unfortunately, they don't give us that, but they do give us the velocity equation. And we know that our position equation is equal to the integral of our velocity equation. I'll refer back to the first slide to see that. Our position function, which is x, is given by the integral of our velocity equation. And that's really it. That's the major concept we have to apply here. This integral is very straightforward. The integral of 4 with respect to time is 4t. the integral of negative 6t squared, we would add 1 to the power, which is 3, and divide by 3, which would make that negative 2t cubed. And then don't forget the ever important plus c. So we almost have our position function. We have almost what we need, except we need to find our c value. And we have a point that we can use to find that c value. But be careful. You're used to a point being x comma y. In this case, when we're dealing with position and velocity and acceleration, we're dealing with points that are written in terms of t comma x. So once you realize that, you'll take 1, plug it in for t. You'll take the 7, plug it in for x on the left side of the equation. And when you solve this equation for c, you'll get 5. So our position function, and it would have been nice had they just given that to us at the beginning, but now we've figured it out, is 4t minus 2t cubed plus 5. And now it's very straightforward. If you want to find the position of the particle at time 2, which is x of 2, we'll just plug in 2 and evaluate, and we'll get negative 3 as the answer. So pretty straightforward. We're applying what we know about position and velocity, getting the equation, and then plugging in whatever number we need to find our answer. Okay, let's take a look at the second example, which is nearly identical to the first one, but it's going to need to be solved in a different manner. So again, we have an object traveling in a straight line, and its position is x of t. We have the initial position at time equals, this is our time here, at time equals 0, our position is 2. And the velocity is given by this equation. What is the position of the object at t equals 3? So exactly the same question from above. We're looking for position, and we need to plug in time equals 3. We don't have our position function, and all we have is our velocity function. You might want to make note of this somewhere on the side maybe, but this second example is a calculator question. I didn't have space to squeeze that in, but this is a calculator question. And the reason I say that is because if we try to integrate this, and you might want to try this and pause and be sure you can do this on your TI-89, but if you try to integrate this function, which is right here, 1 plus x squared to the 1/3 is our velocity equation, that is that. When you try to integrate it with the calculator, you end up with an answer with another integral in it. And then if you actually scroll over, you'll see some other stuff. This is essentially telling you there is no antiderivative. And that's not a problem. We can't solve this second example like the first one because there is no antiderivative for our velocity equation. And again, that's not an issue. You just have to be aware of the different methods for solving these types of problems. And if you remember back in 4.4, when you can't find an antiderivative for whatever reason, an alternate method is to use the fundamental theorem of calculus instead. So that's what we're going to do. So before we actually do this problem, let's actually set that up so you guys can have that version for your future use. If you want to find a position, we're trying to integrate from one time to another time of a velocity function. We know the integral of velocity is position. And since we have bounds, we're using the fundamental theorem of calculus here. Since we have bounds, we'll put a bar. The lower bound's t1, the upper bound's t2. And of course, all we need to do is take the upper bound, plug it in, take the lower bound, plug it in, and subtract those two values. And what we end up with is this. The integral from t1 to t2 of velocity by the fundamental theorem of calculus is the position at time 2 minus the position at time 1. Once you have that little equation and know when you need to use it, we can go ahead and proceed and do this problem. So in this problem, we are given time at 0, and we're trying to find position at time 3. So again, you have to read between the lines a little bit, and that must mean our bounds here are 0 and 3, since those are our times that we're given and what we're dealing with. If we integrate our velocity function, we again end up with position. It'll be position at time 3 minus position at time 0. We know our position at time 0 is 2. We know our velocity function is the cubic root of 1 plus t squared. and we're going to integrate that from 0 to 3. That is just all TI-89. And again, this little screen that you see here already shows what I did in the TI-89, but again, you might want to pause and take the time to see if you can do this. If you need a reminder of how to type this in your calculator, look back at 4.4 for that reminder. If you integrate this function from 0 to 3, you'll end up with 4.51153 equals x of 3, which is what we're looking for, the position at time 3, minus 2. And now it's very simple and straightforward. We'll add 2 to the other side, and of course we're going to follow that 3 decimal rounding rule. The position at time 3 is equal to 6.512. So 2 different ways to essentially do the same kind of problem. So just keep in mind these 2 different methods for solving problems.